Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with the lecture 17 of our Transformers chapter. So today we will discuss about the solutions, assignment 6 solutions, whatever questions I gave you as homework in the previous lecture, all those things we will discuss in today's lecture. So this was the first question. We have to find out the value of I for these two circuits. Okay, seems like a very intriguing like intriguing question, right? Seems like a difficult, but it is not that difficult. So let's first take the first circuit. So if I see over here that we have to identify the value of current I. Okay, so we have to identify the value of current I. So what I observe is, if let's say the current Ix is flowing from here, this current Ix is flowing from here, the same current should flow from here Ix, same current should flow from here Ix. So whatever current is coming from here and here, both are same. So actually in this branch there is no current, I0. In this branch there is no current. So if in this branch there is no current, then here there is no current, then here there is no current, then that means the output this also has no current. So here there is no drop, basically zero current. Okay, so in this first case the current is 0. Now you might have a doubt that will the circuit work? The circuit actually will work as a transformer. Will it work as a transformer? My answer is yes, it will work as a transformer. Why it will work as a transformer? If I tell you that I have a transformer like this, okay, whose primary I am supplying with 100 volt and secondary is open circuited, will you complain that there will not be any voltage induced here? Will you complain? You will not complain, right? You will say, sir, here voltage is getting induced, current is 0, that is fine, but voltage will get induced. So same thing will happen. Although current here is 0, that is fine, but voltage will be induced 200 volts. This is the first lecture, whatever we have discussed, this is the first lecture basically. So if I have a transformer, okay, and secondary is open circuited, right? So flux is flowing through the transformer, correct? Flux is flowing through the transformer. So if flux is flowing through the transformer, if flux is flowing through the transformer, that means I know it is time varying flux, so there will be d phi dt in this winding. If there is d phi dt, voltage will get induced. Yes, current is 0, that means here, right, the current will be only magnetizing current, there will not be any I1 current. That will be the current that will oppose the mmf. It will not, this winding will not create any mmf, just a voltage will get induced. So this will work. Here 100 volts will be here and here 200 volts will be there, totally fine, current will be 0. Okay, now let's solve the second circuit. If I solve the second circuit, just what is the difference? Difference here there was no ground, but here there is ground. So if I assume a current Ix from here, this current will not be actually Ix anymore. This current can be something else as well. Okay, this current can be anything. I don't know what is the current. Okay, for this, right, now I will use the principle of transformer. I know if 100 volt is applied across here, 200 volt will come across here. Now I will use a KVL. I will apply KVL, start from here, go from here, then here, here, and ground to ground KVL, right? So I will go from here to ground. So ground to ground KVL. Okay. Previously I did not had this ground path, so I was not able to apply the KVL basically. I was not able to form a closed loop. But now I have that option. So I will go from ground to ground. This is looking very weird. So let me just remove this. This will be the one, that ground to ground KVL. So let me assume a current over here. So this current is I only. This I current is coming over here and here. So this I current is flowing. So the drop will be, I will be coming like this. So this drop will be plus minus 100 I. Okay. So I will start from here, minus 100 I, then plus 200, then encountering positive first. So this will be plus 100 equals to 0, ground to ground KVL. So my I comes out to be 3 amperes. I comes out to be 3 amperes. So in this question, like, the answer will be 3 amperes, that is done. But what about the other currents? What is the other current? So if I is 3 amperes, what will be the current here? So I is this current, right? I is this current basically. Correct? This is the I current. So here, according to turns ratio, this current will be 2I. So the current through the supply will be I plus 2I, that is 3I. So here what is the current flowing? Here the current is 2I actually. This current is 2I. And here the current is 3I. So actually from here an extra additional current of I will come. Okay. So these are the values basically. So current from the supply will be 9 amperes because I is 3 amperes. Current from the ground will be 3 amperes. And yeah, that's it basically. That's it. And current in the transformer internal here in the primary and secondary transformer, here the current will be 6 amperes. Here the current will be 3 amperes. Okay, very elegant and easy question. Now let's solve this. This was on the polarity test. This was on the polarity test. Let's solve this next question. So it is desired to measure the parameters of a 230 volt 115 volt 2 kVA single phase transformer. The following wattmeters are available in the laboratory. Wattmeter 1 W1, that is 250 10 ampere low power factor. Wattmeter 2, wattmeter 3, wattmeter 4. The wattmeter are used to perform open circuit test and short circuit test of the transformer respectively. Which one shall I choose? So in the open circuit test, what do I find out? In the open circuit test, I find out about no load current, right? And no load loss. So if you remember that this is my magnetizing component, which is generally very large, and this is my core loss component, which is generally very small. So my IO will be somewhere here, correct? And this is the voltage. So the ratio between the rated voltage and the IO is very large, right? If not the ratio, the angle. So phi naught is very high. Phi naught is very high. If phi naught is very high, that means my cos phi naught will be very low. If phi naught is very high, that means cos phi naught will be very low. So actually, this we have not discussed actually. This I did not discuss in the testing of transformer. For a open circuit test, the kind of wattmeter that I will require is, I will require a wattmeter which supports obviously the rated voltage of the secondary, I mean low voltage winding. So 115 volts it should support. Also it should be a low power factor wattmeter. It should not be a high power factor wattmeter. If someone has studied measurement, they will know that if I use a high power factor wattmeter where the power factor of the load is very low, it will cause huge errors in measurement. So we will use a low power factor wattmeter because the phase angle is very high, as my cos phi will be very low. For open circuit test, I will choose a low power factor wattmeter. So either this one or this one. So which one shall I choose? This one or this one? So I know this, that although we perform it 115 volts, but they are telling me what will be the current rating. So no load current will be very low. Okay, it does not matter. No load current will be very low. I can choose W2 actually. We don't need 10 amperes, right? Because I know no load current will be very low. What is the full load current? IFL here, right? If I divide the KVA by the voltage rating in the primary or secondary, whatever you want to choose, I will choose the secondary because secondary will have higher amount of current. So it will be 2 kVA divided by 115. So this value will be 2 divided by 115. So 2000 divided by 2115. So this will be 17.39. Okay, and I know my no load current is like 5 to 10, maximum 2 to 5%, but still if I even take 10% of full load, this is my no load current maximum, right? I am taking maximum 10% of full load, it will be like 1.74 amperes. Still, like I don't need this much amount of current, right? Again it will cause error if I choose a wattmeter reading of higher amperes, but my current is actually not that high. I will have bit of errors. So I should choose a optimal value of current, rated current, so that I can measure the core loss correctly. So I will choose W2 for doing the open circuit test. Now what about the short circuit test? For short circuit test, actually the thing is that generally the leakage flux will be very low compared to the resistance. Okay, generally that is the case. Okay, so for short circuit test, what is happening is X1 will be very less than R1. Okay, so if R1 is greater, I know cos phi is what? Cos phi is R1 by Z. for a series circuit. So this is my series circuit, right? So it is already there, right? Series circuit. So it is R01 divided by Z01. So generally here, right, power factor will be high. So I will choose a high power factor wattmeter. So either this one or this one. In this case, I will actually choose the higher ampere rating. Okay, voltage rating I don't care, because voltage rating anyways will be low, but I will have to choose a higher ampere rating. Why? Because I know that this test will be performed in the high voltage winding, and in the high voltage winding, what is the full load current? In the high voltage winding, the full load current will be 2 kVA divided by 230. So this will be equals to 2000 divided by 230. So this will be 8.69 695 amperes. So of course, like it is almost 10 amperes. So I cannot choose a 5 ampere, right? Because in the high voltage winding itself, the full load current is more than 5 amperes. So 5 amperes is not possible. I have to choose W3 only. So W2 and W3, that is present in the option D. So option D will be the correct answer for this particular question. So now let's move on to the next question. So in the next question, we have this 10 kVA transformer. Open circuit test and short circuit test are performed, and the following are the results of the test. Determine the efficiency of the transformer at half full load and 0.8 power factor. So what is efficiency? If you remember, efficiency, right, was equals to X into S rated cos phi divided by, so let me write SR only, okay, else this will be long. So this will be SR cos phi plus X square. I am not telling you to remember the formula. I know, right? I know what does this mean. I'm not telling you to remember the formula. I'm just going by the concept. Input is X SR cos phi, because this is the power input. Sorry, this is the power output. Okay, and this is the output plus the losses. Losses is the copper loss, PCUFL plus the coal loss. So you don't blindly mug this one up. You understand what does each term means. Okay, then this will be easier for you to remember. So it is half load. So it is, if it is half load, so X will be half. SR is what? SR is 10 kVA. SR is 10 kVA. And cos phi is 0.8 lagging. Cos phi is 0.8 lagging. So cos phi will be 0.8 lagging. Okay, so my efficiency of the transformer, this will be 0.5 into SR, that is 10 kVA, into cos phi, that is 0.8, divided by X into 10 into 0.8 only, into X square, so half whole square, into PCUFL. What is PCUFL? PCUFL will be obtained in the short circuit test. So if I see, the short circuit current is actually 3 amperes. Now is it the full load current? Is it the full load current? Because short circuit, we have to identify, right, whether we are applying the full load current or not. We have to identify. So if I see here, what is my full load current? Like we're operating in the, obviously in the in the high voltage winding. So IFL in the high voltage winding will be this will be equals to the kVA rating 10 into 10 cube divided by the voltage. Voltage is 2500. So if I observe that 2 zeros are going here, so this is actually 4 amperes. So we are not actually applying the rated current. We are not applying the rated current. So there is a problem. I know the copper loss at any load will be X square into PCUFL. Correct? I know the copper loss when my X is what? X is equals to, what is X? Full load current is 4 amperes, but I am applying 3 amperes of current. So it is 0.75. So from here I will be able to find out my PCUFL. So PCUFL will be equals to PCU, that is 45. So the power is 45 watts. So 45 divided by the X square. So this will be 3 by 4 whole square. So this will be basically 16 divided by 9. So 9. So 9 is 5. 5 into 16. this is 80 watts. So PCUFL will be 80 watts. Okay, but I actually don't need 80 watts. I have to multiply here 80, right? That's what I needed for. And what is my P core? So let's check if I am applying rated voltage or not. Yes, I am applying rated voltage. That is fine. So this will be the rated core loss only. So this will be 50. But everything here, remember, everything here is in kilowatts. Or okay. This was all in kilowatts. So this also should be in kilowatts only. So this, right, I can add 50 and then divide by 1000 or 10 raised to power minus 3 to convert this into kilowatts. That's it. So this value will be into 100. Have they asked in percentage? Okay, they have asked in percentage. So I have to multiply in 100 percentage. So this value, right, will basically be this will be 5 into 0.8. So this is 4 divided by 4 plus this is 20 plus 50. So this is 70 or 0.07 into 100. So 4 divided by 4.07. So we'll quickly calculate this value. What is 4 divided by 4.07 into 100? So 98.28 percentage. 98.28 percentage will be the answer of this question. So that is present in option C. So these were actually very close. So you cannot actually make any approximations. So this was a ESC question. So let's solve the next question. So in this question, we are performing the following test. So in 50 hertz, open circuit test is given and short circuit test is given in the high voltage low voltage side. In 40 hertz, open circuit test is given and short circuit test is given. Now what are they asking? It is assumed that the no load components of the no load components, hysteresis loss and eddy current loss are equally divided. Then W1 and W2 will be. Okay, what is W1? So W2 is here and W1 is here. So initially I am performing my test in 50 hertz. Now if I am performing my test in 40 hertz, what will be the values basically? That is what they are asking. Okay. So we have to think about this. So will I be able to find out the full load copper loss? Because my copper loss actually does not depend on the frequency. It purely depends on the current only. So let's first discuss about the short circuit current. So here the short circuit current is 5 amperes. So what is my full load current? So this is performed in the high voltage side. In the high voltage side, what is the full load current? Okay, so the full load current will be 1 into 10 cube divided by the kVA rating divided by the voltage in the high voltage side 200. So this will be cancelled 10 by 2. So this is 5 amperes. So actually here I am applying the full load short circuit current only. So PCUFL is actually 25 watts. Now the short circuit test, if you see, notice that it is being performed in the low voltage side. So in the low voltage side, what is the full load current? Low voltage side, the full load current will be 1 into 10 cube divided by 100. So this will be 10 amperes. So actually in the low voltage side also I am applying full load current only. So obviously the copper loss will not change. It is basically the full load copper loss. If I perform it in the secondary low voltage side or the high voltage side, it will be same. So it will remain at 25 watts only. It will not change. So copper loss will not change. Copper loss will be 25 watts only. So option A and D are the possible answers. Now let's check for the first case. So in the first case, open circuit test, applied voltage is 100 and here applied voltage is 160. Okay. What is V by F ratio? So initial V by F ratio is 100 divided by the frequency, that is 50, right? 50. And here the secondary V by F dash ratio will be 160 divided by the 40. So this will be actually 4 and here V by F is only 2. So V by F, right, has been changed now. If I notice, V by F has been changed. Okay. So now, is it correct? V by F hasn't changed. No. Actually, I'm operating in the now I'm operating in the high voltage side. Okay, so I have to compare the high voltage side voltage. Sorry, I made a mistake here. What is the mistake? This test was performed in the LV side, right? And now I'm performing the test in the HV side. So actually, I have to take the referred voltage on the LV side. Okay, I cannot take the HV side voltage, because here the initial test was performed in the LV side. So here also I have to take the voltage from the LV side only, not on the HV side. Otherwise, I will make a mistake. Okay, otherwise I will make a mistake now. Like if you want to compare, you have to compare the voltages both, if both voltages are with respect to LV side or with respect to HV side. You cannot compare one with respect to LV side and other with respect to HV side. Then of course your V by F ratio will come different. Just be careful. This is actually very good concept question. Okay, so here I have to compare, although the voltage here is 160, but it is applied in HV side. So in LV side, what will be the voltage? It will be 80. So now if I compare my VF upon F dash, this will be 80 upon 40. So that is constant. So the flux, right, BM, flux density is constant. It will not change. So if flux density is not changing, what is changing? Frequency is changing, right? So I know my, in case of iron loss, okay, coal loss, hysteresis loss, it is proportional to F, and in case of eddy current loss, it is proportional to F square if the flux density is constant. And also they have told me that initially it is assumed that the no load loss components, hysteresis loss and eddy current loss, are equally divided. So here it are equally divided. So here my Pi plus Pe will be 20 watts. So Pi plus Pe will be 20 watts, as we can see in when the power was here, like when open circuit test was performed, it was 20 watts. So from here I can directly say, like it will be either 2 Pi, because both are same 20 watts. So I can directly say that Pi is 10 watts. Okay, Pi is 10 watts. Okay, so Pi I got as 10 watts. Pe is also same, that is 10 watts only. Pe is 10 watts only. So right now my flux density is constant. So what I can comment is that Pi changes with frequency. So if initial Pi was this, what will be Pi dash? So Pi by Pi, Pi dash by Pi will just change with frequency. It will be it is proportional to frequency, right? Okay, so if it is proportional to frequency, so it will be F dash upon F. So what is F dash upon F? F dash is the new frequency, that is 40 hertz, old frequency is 50. So what is Pi? Pi is 10 watts. So it will be Pi dash will be 8 watts. So the hysteresis loss will be 8 watts. What about the eddy current loss? So eddy current loss is proportional to the square of frequency. So Pe dash by Pe will be F dash whole square divided by F square. So Pe dash divided by P is 10 watts again, and it is F dash is 40 divided by 50 whole square. So it is 4 by 5 whole square. So it is 0.64. So my Pe is, P dash is 6.4 watts. So overall iron loss will be how much? Overall iron loss I have to calculate. So overall iron loss will be the addition of these two numbers. So overall loss, iron loss, P core will be 8 plus 6.4, that is 14.4 watts. Okay, so it will be 14.4 watts, that is present in option D. So option D will be the correct answer of this question. W1 will read 14.4 and W2 will read 25. Just be careful here. I know there will be confusion. How did I choose voltage to be 80? Why I did not choose voltage to be 160? Why I did not choose voltage to be 160? So if I am comparing V by F, right, I should always compare with respect to the same side, either the high voltage side or the low voltage side. Otherwise there will be a problem, because the frequency does not get scaled as I move sides, voltage do. Okay, voltage does get scaled as I move sides, right? So the problem is, in the equation of flux, it was equals to E1 upon root 2 pi f into N1. So this number of turns was also there. So actually that's why my flux, right, or Bm is not always proportional to E1 by f. It is proportional to E1 by f into N1. Okay, so that's why N1 is also there. I am ignoring the fact. So if I am comparing in the primary side, I have to compare in the primary side only, because then only the N1 will be constant. Else if I just compare, let's say this is the N1 is the high voltage winding and N2 is the low voltage winding. So if I compare in the low voltage winding, this will be V2 upon F into N2. Okay, so flux will remain constant only if I write the N2 value. Okay, I mean, what do I mean is, here Bm is actually proportional to this, right? So here I am just comparing the ratio of voltage and frequency. I am not taking into effect the turns. If I am not taking into effect the terms, assumption is the number of turns is constant here and here. But you have a problem. You are comparing the voltage in the low, high, here, right? You are comparing the voltage in the high voltage winding. Here the voltage is in the low voltage winding. So number of turns has changed. Here the number of turns will be NLV. Here number of turns will be NHV. So you have to take into effect. If you don't want to take into effect the number of turns in the HV, that means you refer the voltage into the low voltage side and then you compare, because then here also number of turns will be in the LV, here also number of turns will be in the LV. So assumption is that N remains constant, so my flux only depends on voltage and frequency. Got it? That's why we must compare. If I comparing V by F ratio, we must think that we are either comparing with respect to primary or secondary for both the cases, because it depends on number of turns as well. But I assumed internally that N1 is constant, it is not varying, but actually here it is varying, because first initially it was NLV, now it is NHV. So number of turns is changing. That's why it is important to compare with the same side, either HV or LV. Okay, I hope this confusion got cleared, and I know no one in this whole industry will explain you like this. Trust me, in this whole gate industry, no one will explain you these things. Okay, no one will tell you these things. Trust me, like the dropper students will know. If they have done this kind of questions, they will not even take this kind of questions. Okay, so let's solve this question. A 10 kVA 500 250 volt single phase transformer was tested, and the following results were obtained. This is the short circuit test. This is the, and they are asking me, it is given that the maximum efficiency occurs at unity power factor and 1.2 times the full load current. So actually it occurs more than the full load current. So that is a possibility. So basically efficiency is maximum at x equals to 1.2 times the full load current. Okay, that is what my efficiency is. So my x, right, x is equals to what? So also if it is given maximum efficiency occurs at this, the maximum efficiency of the transformer they are asking and the full load efficiency. So x is what? If you remember, the maximum, we get the condition for maximum efficiency when the coal loss and the copper loss are equal. That is, my x square into PCUFL will be equals to the coal loss, right? Variable loss is equals to the constant loss. So from here, do I know PCUFL? So short circuit test is given. So short circuit current is 20 amperes in the high voltage side. So what is the full load current in the high voltage side? So IFL in the high voltage side will be the high voltage kVA divided by the voltage. This will be 500. Okay, so this value will be 100 divided by 5. So this is 20 amperes. Actually, whatever the current we are applying, it is the rated current only. So this loss is the PCUFL. Okay, I know that x is 1.2, right? X is 1.2. So it will be 1.2 whole square into PCUFL, that is 150, will be equals to my coal loss. So I get the value of my coal loss. So coal loss value will be 1.2 whole square 1.2 whole square into 150 216 watts. Okay, coal loss will be 216 watts. Okay, now what do we need to do now? Basically we have to find out the maximum efficiency. What will be the maximum efficiency? Maximum, like, what is the efficiency formula? It is x into SR cos phi divided by x into SR cos phi plus x square into PCUFL plus P core, right? Cos phi is 1, x is 1.2 and SR is 10 kVA. So this will be 1.2 into 10 into 1, this will be 12 plus the x square PCUFL. So like in maximum efficiency both these terms are equal, right? So it is simply equals to 2 into Pi, same, right? 2 into Pi. Pi is 216 watts. I want to write it in kilowatts because everything is in kilo, into 100. Okay, will give me the percentage. So this will be 12 plus 0.432 into 12 into 100. So this is 96.525%. Okay, this is the efficiency, maximum efficiency. Now they are asking me the efficiency at 0.8 power factor at full load. So full load meaning my x, this is maximum, that x equals to 1.2 and cos phi is 0.8. Now my x is 1 full load and cos phi, sorry, here cos phi is 1, cos phi here is 0.8. So I can find out the value. So this will be what? X is 1 into SR is 10 into cos phi is 0.8 divided by 8 plus, now what is x square PCUFL? So x square is 0.8 whole square into PCUFL. What is PCUFL? PCUFL is this value 150 watt, correct, or 0.15 in kilowatts. So this is my PCUFL. So this will actually come here. And plus the iron loss will be constant, that is 0.216 into 100%. Okay, so from here I can easily find out the values. So this will be 0.8 whole square into 0.15 plus 0.216 minus 0.3, sorry 0.8 whole square into 0.15 plus 0.216. so this is efficiency, this will be 8 divided by 8 plus 0.312 into 100%. So this will be plus 8 into 8, so into 100, that is 96.24%. Okay, so efficiency at this particular load will be 96.24%. Okay, am I correct? Yes, this should be correct because this is the maximum efficiency. I'll just quickly calculate whatever I have calculated is correct or not, right? 0.8 whole square into 0.15, just 0.8 whole square into 0.15. Why is it 0.15? 0.15 is the full load copper loss. Okay, 0.8 whole square into 0.15, yeah, this is 0.096 and the iron loss is 216, right? 0.216, so it is 0.216. So yeah, it is 0.312 only, whatever I have calculated is correct only. Okay, so this plus 8 inverse into 8 into 100, yeah, this is correct. So this is the answer of the question basically. Okay, so that's it basically for this lecture. I hope you have enjoyed this lecture, and next lecture will be the last lecture of module 1, where we have covered the whole single phase transformer. Everything has been covered in full details, nothing has been left out. So yeah, make sure to give a review. That's the only demand from us. So yeah, I will see you in the next lecture. Until then, happy learning.